Good evening to all of you. In this lecture, I will discuss mobile communication system. We'll start with this topic. And in this topic, the first concept is the cellular concept. As many of you are aware of, that the current mobile communication is based on the cellular concept, wherein the service area, the service region is divided into different cells, and those cells are governed by or managed by the base station. Base station is responsible for controlling and allocating the resources to mobile stations. So whenever a mobile station wants to contact another mobile station, whether within the cell area or outside the cell area, it has to first communicate with the base station. And then the base station, it's not only has an hardware associated with it, has the software which control the communication and facilitate the communication. So whenever, because of this cellular infrastructure, mobility is being offered to the users. They can be mobile, they can move from one cell to the another cell. So in a way, the communication is being governed through the cellular infrastructure. Both physical hardware is involved, and the software is also involved. We'll deal with both the parts in detail as and when we'll focus on individual communication technologies. So here today, the first concept, we'll see that how to create the cells, uh, what would be the size of the cell. So as a service provider, imagine as a service provider, if you've been allocated a set of frequencies, and is being allocated to you, that for example, suppose there is a service provider X who has to govern, who has to provide service to its mobile users in a particular area. So first, he has to work on the infrastructure, and the primary focus would be on the creation of the cells. How that region would be divided into different cells. There are several parameters which governs the design of the cells. First, we will see that what should be the shape and size of the cell. Cell area we will see. Ideally, if you will see that if we have to govern the mobile stations which are mobile, so we have a transceiver intact as a base station right at the center, and obviously transceiver would deal with the mobile station using signals. So signal communication, radio communication would be on in between the mobile station and the base station. Base station is to govern allocating the necessary resources for proper communication in between mobile station to base station and mobile station to mobile station. So for that purpose, we have a static base station. Right now, we're dealing only with the static base station. Base stations can be mobile as well. In ad hoc networks, you will see those base stations can be mobile as well. But here, in general, in practical, mostly we deal with the static base stations, which are placed by the service provider somewhere to facilitate the communication within that cellular region. Ideally, because as we know that if there is no attenuation, no interference, nothing is there, then obviously the signal strength would decrease proportional to the inverse of the distance from the base station. But in reality, if you will see, there are several parameters which would impact the signal strength. We have seen reflection, reflection, uh, and there are several more blocking, and uh, and the reason being is that the terrain is not same. There are several hindrances, and because of that, as you can see in the B, ideally we are assuming that the region based on the signal strength decay, if you would see, should be circular in shape, but because of the distortion to the signal strength, the region would be somewhat distorted. So this is just to explain that in actual, when you will design, when you will create the cell, so obviously we are hoping that the ideal cell should be circular in nature, but because of the hindrances, because of the interference, somewhere the circular nature being distorted, and we will get something like this. When we will discuss on theoretical grounds, so the cellular design. So there are different models comes in place, and the first is this is hexagonal, which is more appropriate to use because of its closeness to the circle. When we will divide our region on papers, so we can use this model, the hexagonal model, to discuss several parameters, to plan our frequencies, which cell would use which frequencies. So we can use any one of these three or any one other apart from that, and this is just for representation purpose. But these are those models when we will play with our resource allocation, when we will do the groundwork on paper. So the near approximation to this ideal cell is the hexagonal cell, which is generally being used because it allows you to first approximate it with the idealized cell or the circular cell. So the behavior of the signals which we can assume, which we can get in the ideal cell, somewhere those things we can simulate to in the hexagonal as well. But apart from that also, we can have a model, the rectangular model and this triangular model as well. This is just to walk with the frequency allocation and dividing our whole region into different cells. Now we will see that if the shape of the cell is a square, let's suppose we are doing a paper work, and the shape of the cell is a square. So the side, um, each side is of length r, so the area is r square. The parameter would be 4r. So if you would see that the boundary length, so this is one parameter, so these are the parameters in which we will further talk about the technologies pertaining to the cellular concept. So what is the boundary length per unit area? So that would be 4 by r, because 4r divided by r square, this is the boundary length per unit area. So this is also one parameter. All these parameters would impact handoffs. All these parameters has certain importance further when we will start discussing about the technologies, that what is the boundary length per unit area. So your area is r square and the boundary length is 4r. So it is 4r divided by r square, that is 4 by r. So this is one parameter. Then what is the channels? How many channels per unit area with n channels per cell? Channel means at a time. So if I'm mentioning that in a cell n channels are permitted, so your base station can manage only n users at a time. So it has only n channels which it can allocate to an individuals who are mobile users. So here another parameter is what is the number of how many channels are there per unit area with n channels. So in a given cell there are only n channels permitted. So during that circumstances, what is the number of channels per unit area? So obviously the area is of a circle is r square, and you have n channels, so n divided by r square. So this is also one parameter. So that defines obviously that our aim is within a region there must be maximum number of channels. So this is also one parameter, that per unit area how many channels are there in a particular cell. Then the next one is if you will increase the number of channels by a proportion or by a factor of k, what would be the new channel allocation? So you are increasing number of channels. That means either you are increasing your frequency range, or if you are using some other technology, so you are increasing your uh, channel count by a factor of k. Then what would be the new uh, channels per unit area? That is kn by a factor of k. If you will increase the number of channels n, that is kn, then the new channels would be kn divided by r square. The same impact why they have done it, to instead of increasing the count of channels, if we will decrease the area, if we will shrink the area, what would be the impact? See, here if suppose the area is r square, we are decreasing this length, the length of the square we are decreasing by a factor of m. That means if currently the length is r, the next cell would be of length r by m. So in that situation, what would be the channel count per unit area? So in this way, n divided by r by m whole square. So m square will go as a numerator. So m square divided by r square. So you always have two options. If suppose uh, the offered load in a cell is increasing, as a service provider you have two options. Either you can allocate more resource in terms of frequency range, in terms of another technology. If you are using, like suppose if you are using CDMA, give more code space. If you are using time division multiplexing, then allocate means divide your time into many more number of slots. So that is one way. Another way is to reduce it, to actually shrink your cell. To shrink your cell, when you will shrink your cell, so obviously per unit area the channel allocation would be more, because in a way, uh, if you would notice it, you are reducing the number of users within the cell. Now the additional users who were initially interfering with you and who were demanding more resource, you are taking them out. You will manage them in some other way, but this is the way of actually balancing your load. If you would not be able to handle many more clients, many more users who are approaching the base station, then base stations have two options: either to allocate more resource, so to have more frequency range to allocate or to entertain the request, or otherwise shrink the size. Then per unit area, you would have more number of channels. So the same in this table, they have done it for all other models as well: hexagonal, circular, triangular. The same thing they have done it. So these are the important parameters pertaining to any cell. So what is its area? What is its boundary? Then what is the boundary length? per unit area. Another parameter is how many channels are there per unit area, and if you will increase the channel count, what would be the new channel count per unit area. And another one is if you will shrink the length, if you will reduce the cell size, and that phenomena is called breathing. So you are letting your cell to breathe, because if the overload would be more, your cell would not be able to breathe properly, would not be able to function properly. So to let your your cell breathe, you are shrinking its size. So that is called breathing, cellular breathing. So that is one thing. Then now here we will understand the next concept of hands off. Uh, that is called hands over as well. So suppose there are two cells, cell I and cell J, and you can hear, so here we are initially considering the idealized cell, means the circular in shape. So here you can see the signal strength, contours for both the cells, cell I and cell J. So here, and so this minus 60 decibel milliwatt. So dBm is a unit of a signal strength. That means if the cell I base station would generate a signal using 1 milliwatt signal strength. So in decibel, so what would be the power ratio? So that we are calculating in decibel. So minus 60 decibel, very near to the base station, then minus 70, minus 80, minus 90, minus 100. So obviously there comes a point where onwards signal strength would be so less, and that would start acting as a noise, would be of no consequence to the receiver. Likewise, you have a cell here, cell J, minus 60, minus 70, minus 80, minus 90, 100. Now the aim is that if, like, suppose there is a user, that user receiver would pick the cell I base tower or the cell J base tower. Your user is mobile, so that user would start receiving the signal strength, both signal strength the receiver is receiving. So where the mobile user would linger on, would start communicating with. So that is called so that's the thing which needs to be solved. So here we will understand the hands over through this. So this is the idealized behavior of the signals. But as we know, because of the attenuation and several other constraints, so this is something which would be actual. So cell I and the cell J. And as we know that, as here also I have explained you that as you go far, your signal would decay in terms of strength. And as we know that decay based on the distance is inverse to the square. So here in this graph you can see the received power px, so x is the distance from the base station, so it would follow the inverse law. The received power would be inversely proportional to the distance. Now we will understand the hands off. Hands off means that whenever any user, mobile user, is moving, so, and there are two received powers, there are two base stations which can support the communication. At what time the transceiver of mobile station would pick the next one? So initially, if there are two cell I and cell j, initially the user is within the range of cell I and is moving towards cell j. So at what time the mobile user would leave the contact with cell I base station and would start the communication and would pick a communication with cell J. So that depends on the signal strength, how much signal the receiver, transceiver of the mobile station is receiving. So here you can see that there is a base station, and for the signal strength due to the, so on this axis there is a signal strength due to base station I, and on the right side there is a signal strength due to base station J, and this is the distance in between. So base station I and base station J at xi distance, you can see um, the received the signal strength received due to base station J is almost nil, and likewise at x2 the power received the signal received due to base station I would be almost nil, and at both these points due to base station I the power is maximum, and due to base station J the power is maximum here at x2. Now there is a base, the mobile station, which is moving towards base station J. So at x3, suppose your mobile station is starting. So at x3, when mobile station has to pick up a communication, so obviously mobile station is under much more influence with the base station I in comparison to base station J. So your mobile station